Hello, today I'm going to be talking about constant velocity motion. So first we're going to have fundamental physics principles. We're going to talk about the introduction. We're going to have analysis of the ball. We're going to compare models and graphs, do a code analysis, and then finally talk about what if and human error. So first we have to utilize two fundamental laws and equations, Newton's second law and the position update formula, as shown. So the purpose of this law is to utilize our knowledge of Newton's second law to construct a computational model which predicts position versus time. We will then compare this model to the actual position versus time using a graph. We hope to further our understanding of Newton's second law in real-world situations, rather than just textbook-based problems. So let's talk about force diagrams. So obviously, if a ball speed is increasing and the ball is moving to the left, there will be applied force to the left, along with the normal force and force due to gravity. But in our case, we're going to assume that there's no net force and that the speed remains constant, which means there'd just be normal force and force due to gravity. For this experiment, we're going to assume that air resistance and friction do not act on the ball, which is obviously not true. So here's how I derived that final velocity is equal to initial velocity. First, I have the net force is equal to change in momentum over change in time. We put that into a formula. Then we divide F net times delta T over delta P by the mass. And then we get final velocity is equal to initial velocity plus net force over mass times delta T. Since net force is equal to 0, we can discard that into the right of the graph. So we just get, or the equation. So we get final velocity is equal to initial velocity. So the system is just the ball and the surrounding is everything else, including the ledge in which the ball is rolled on. The initial conditions that we need to find are the initial velocity and position. We know that the initial velocity, or the initial position is just x equals 0. So now this is analysis of the tennis ball's motion during tracker. So obviously it's moving to the left, so there will be a negative slope as shown. This is our data. So now our computational model, we need the initial velocity, the time, the change in time, the velocity update formula, and the position update formula. So we're going to find that. We can find these constants. So the change in time is just 4.6 seconds because that is the time when the ball started rolling to the end of the video. And then the initial velocity is just equal to the average velocity, which is change in position over change in time. So that's negative 96.6 centimeters over 4.6 seconds, which is negative 0.21 meters per second. So obviously now we're going to see the model in action that we built. So this is the model. It has a slope very similar to negative 0.21. So this is the data from our model. So these are our two line graphs. So the predicted is the blue one, and the observed one using tracker is the red graph. So I think that the difference in the predicted versus observed position versus time graph exists due to human error, such as me not using tracker correctly and not placing my center of masses actually at the center of the mass of the ball. So that might be a problem. Also, there's forces such as the force of friction acting on the ball in the real life example, which we disregard in the model. So what if the axes were flipped? I chose to use a conventional x-axis where negative x would be to the left and x would be to the right. Knowing this, the velocity was negative, which meant that the slope of the position time graph was negative as shown by the line graph. If I flip the axis, this would mean that the negative x would be towards the right and the positive x would be towards the left. As a result, since the ball is moving to the left, the velocity would be positive and the slope of the position time graph would simply be the absolute value of the original negative slope. So what does it mean? When we assume that net force is equal to 0, can we determine the number of pushes and pulls on an object? No, because every single object exerts gravitational force on the ball and vice versa in the system. As a result, there could be an infinite number of forces acting on the ball, which means we truly cannot determine the number of pushes and pulls on the object ourselves. Thank you.